Okay, so very warm welcome to all of you in this asset colloquium. It's a real pleasure to have with us Dr. Andre David and Dr. Raghunandan Shukla with us to deliver this special asset colloquium. A few words about our speakers. So, Dr. Andre David, he says he first entered CERN hostel for the first time in 2000. He's currently serves as a senior staff physicist at CERN, focusing on the HGCAL, and he leads the section on the CERN CMS team. He's also an invited professor at the School of Engineering in the University of Lisbon. So he did his PhD on a fixed target experiment, NA60, where he worked on pixels and microstrip silicon detectors. He joined CMS in 2006 and he led the commissioning of the CMS HGCAL. Thereafter, he was one of the key players in the discovery Higgs analysis in the diphoton channel. That's where I know most of his work from. And he went on to do many things in Higgs, including leading the Higgs group as a convener. And in the recent, maybe around 5 years, all his efforts are focused on the GCAL. So, yeah, he is really a master of many trades. We also have with us Dr. Raghunandan Shukla, who of course is no stranger to TIFR. He was a scientific officer here. And he has been involved in very detailed designs while he was in TIFR of the previous iteration of the back-end boards. But some of you may know, but he also served to operationalize a triggerless DAQ system at the GRAPES 3 experiment, or contributed to it. And in the recent past, he's deeply involved in writing firmwares and operationalizing the back-end systems and playing a lead role in many of the test beams and system tests to make sure that this beautiful detector actually comes to reality. So without further ado, I welcome them warmly to deliver this asset colloquium. First, Dr. David will start the talk and Raghu will follow him. Thank you.
Thank you, Rajdeep. And thank you all for coming. Next. We don't like it. Do we have to be on the other screen? We might have to be here. We go back. There you go. So it's the proverbial question, how many PhDs does it take to make a computer work? So the way this is going to go is that you will be very kind, because both Raghu and I and Irfan and also Professor Mohanty, we have been on a trip to visit suppliers. And yesterday we missed the flight by this much. So we are all very tired, slightly confused, and we are still trying to get our bearings back. I am going to tell you a bit more about the high-Lumi LHC and about this detector. And then Raghu was kind enough to go into the details of the electronics that we are building. And then I will tell you again a little more about the system tests that we have done. So the LHC is the Lord of the Collider rings. I'm sure many of you have heard about it, and how there is a lake, and there is cheese and cows and the Alps. What I would like you to know is that it's big. It's really big, and it encompasses basically the whole of South Mumbai. And Mumbai is not small, like everyone who comes to TIFR knows. It's like you're in Mumbai and then you still have to go all the other half into the middle of the naval bases. Now, 14 years ago, we discovered a new boson at the LHC. At the time, we didn't know if it was a Higgs boson or not. We've actually learned a few things, but we've only scratched the surface. So we have not measured all of its properties, and I'm not going to delve into much of the theory. Well, there will be an equation later on, but it's the linchpin for a lot of the standard model of particle physics, which is a theory that has both a beautiful cathedral and an incredibly dirty, strange slums, which is the Yukawa sector. Now, the LHC is going to continue, especially because we want to learn much more about the Higgs boson. And you will see that we are about to enter the long shutdown 3. This is a period where the detectors will undergo substantial upgrades, and they will operate up until 2041. So all of you in this room will have been able to get a PhD by that time. Okay? And even people who are in high school, and even people who are in middle school, they can also come and contribute. It's going to be a very long journey. Now, what we are going to do in order to be able to study the Higgs boson better and also to extend our reach for searches is to make more collisions per unit time. So we are going to have 200 simultaneous proton-proton collisions on average every 25 nanoseconds for more than 10 years. So this means that the detectors are going to withstand much more radiation, and we are going to have many more particles produced at the same time. So we need to have better granularity, better resolution in order to be able to separate and measure them individually. So this challenge we are going to face by improving timing measurements, by having better spatial resolution, and by having more information at the trigger level. So this is something that Dr. Shukla will be discussing, is how do we compute all of this information and have an answer within 12 microseconds. Now, all of this is because of equations, right? So we like to have some input from theory, and in particular, the standard model makes a very clear prediction as to what the Higgs boson should do. So these terms, we actually have one since 2012. And then, which is basically, we've measured the mass of the Higgs boson, so we can connect that to the field. And then there is a quartic interaction, where you have 4 Higgs field lines connecting. This is well beyond the lifetime of the high-lumi LHC. I think that even the FCC might not be able to tell much about it. But there is this term, which is the trilinear term, or also known as the Higgs self-interaction. This is the one that we actually want to build a detector for. And of course, it's a detector that should do this, but like the 2 general purpose detectors at the LHC, they are built for whatever nature throws at us. And here the detector has to be thought of, has to be conceived as not just the physical thing that is on the table, but all of the electronics and all of the logic that is programmed into the electronics to select which collisions to keep and which ones to throw away, because we throw away a lot of collisions. It's a very wasteful, actually, the important thing is to be able to select the ones that are interesting. And in that sense, we have actually, in the last 30 years, been making more collisions with more or less the same amount of electricity. So it's even become more energetically efficient. Now, there were people already thinking about this 25 years ago. So I had already started my PhD, but many of you in this room had a negative age. So I don't know if your parents had even met. But there were people who were already thinking, what do we need to do in order to go beyond what the accelerator that we are building provides? So this was in 2002, and there was already a very clear conclusion that you have to completely rebuild certain detectors. This we knew because we knew that the technology, for instance, for silicon, cannot withstand more than a certain amount of radiation. The silicon just breaks down in a way, so you cannot get the electrical signals from the particles going through. In the meanwhile, there were many plans, and in the last 10 years, CMS has gone through making this concrete. So these are all the technical design reports for the different upgrades of the detector. And now I will just go through them one by one. So this is a view of the CMS detector. The part in purple is the solenoid, which is the S in CMS. And we start with the inner tracker. So this is going to be a completely new inner tracker, as was predicted 25 years ago. Then we are going to refurbish the barrel calorimeter. We're going to remove all of the electronics, but keep the lead tungstate crystals. Then the muon system will go to higher rapidity. They will cover a bigger range, and it will be tolerant to much more rate. There is also going to be a completely new system for the readouts. We have a larger latency to decide whether or not to keep the data, and we will be able to, let's say, analyze 750,000 high-resolution pictures from the detector per second. Then one of the things that we found out was that we really have to throw away the calorimeter in the end caps. It's spent. The crystals that are transparent or were transparent are now milky. They are like yellow milky. There's no more light. They produce the light, but the light gets absorbed before we can detect it. So we have to really throw it away and make a completely new one. And then there are some additions. So there's a new detector for measuring the timing of charged particles. So you can go one by one, the charged particles, and tell what time they cross the detector, so which collision they came from. And basically, there are also some other additions to bring radiation and precision proton spectroscopy. But basically, what we are trying to do is that if you only take the picture in space of all of these 200 collisions, everything is on top of each other. But since the beams are crossing, the collisions happen at different times. And so by adding the time dimension, you just want to spread these out. And when you measure the time, you actually start to see all of the different collisions happening in different places in space-time. So now you know that this was a collision because it happened at this time. And the same collision in the same place, there's a collision here in the same place, but it happened at a different time. So you basically pull out this picture, and by doing that, you can reduce the density of collisions more or less to the same levels we have today by adding the timing information. And then if you have a calorimeter that is also able to do the same thing, because photons do not leave a charged track, you can then say, but these photons come from this particular collision because these are the hypotheses that are compatible with the timing of the photon. So if you have these two photons, you know that the two photons came from this collision and not that, and not that, and not any of the other possibilities. So it is important not just to have the timing for the charged particles, but also for the neutral particles. Now, one of the things that everyone is going to tell you is that, the LHC is a proton-proton collider, and they have ions. Let's not forget that. But this is not completely true, because protons are just big bags of elementary particles. And in fact, the harder you look inside the proton, more elementary particles start coming out with higher energies, because the more energy you put in to look inside, the more stuff starts to come out. So in fact, all of these interactions are relevant interactions for the production of Higgs bosons and for production of pairs of Higgs bosons. That comes back to this. You see, for instance, this vertex in green, it's where 3 Higgs bosons meet. So this is not where 3 Higgs bosons meet. This is the VVHH vertex. But this interaction in particular, this is the one that we want to nail down at the LHC. And if we can go and look, you will notice that there are many interactions here where you produce a quark and an antiquark, or here, well, not here. But if we can find these particular jets from the quarks, this means we can enrich our sample in this type of interactions. And in this case, we can actually transform the LHC not from just any proton-proton collision, but into something which is, for instance, collisions between vector bosons. Here, you see, these are vector bosons that are being emitted. So we are transforming the LHC, we are enriching the sample of data that we get from the LHC in this type of collisions. In order to do that, so let's take here the case of producing, you see the two vector bosons producing a Higgs boson and then a decay into two photons. And we can follow in the detector what happens. So you see the photon interacts in the first few layers, because this is the electromagnetic section. We have to design it like that. And then you have the jet of particles going through. So if you have very high spatial resolution, you can separate these objects very nicely. But the problem is that if you now add everything else that happens in the 200 collisions, you get all of this. And now what you need to do is, if you use the time dimension and you just select a 90 picosecond wide window, you can remove all of the pileup hits, and you can very clearly see, or, and you can also perform better measurements of the photon and the jet. So this way, we can enrich our sample in all of these processes here, which will give us many more interesting probes into the Higgs boson. In particular, with all these interactions with vector bosons, which is the beautiful side of the standard model. We should also study the dirty side, but we need to make sure that the beautiful side is there. So this is where the talk actually starts after this introduction. It's what are we going to do with all of this data that is being purified in vector boson interactions? And yes, it will also include, this talk will also tell you why all of these things are hexagons. Because for those of you who know CGP gray, hexagons are, there we go, exactly. I will make sure to get a chocolate. All right, so what are we going to do? So the detector is very complicated. It's complicated for several reasons. First, because we want to have a lot of channels in order to be able to see all of these pieces. It's complicated because it lives in a very difficult radiation environment. The challenges are basically four for this detector. One is to be able to measure energies all the way from the single particle going through the detector, that's where we calibrate, all the way to 10,000 particles from a photon shower or a high energy electron shower. We also want to have many cells. So the detector is going to have 6 million channels, and this is why everything has to fit together in a very funny way, because we want to have lots of sampling layers to know how the shower has been developing. We want to have a timing precision of the order of 30 picoseconds in order to be able to distinguish the different interactions and say, where are these particles coming from? And there is a challenge, which is a computational challenge. And you will hear from Dr. Shukla how this is done online. And then I will tell you more about how it's done offline, how to put all of this together. How do you bring to fruition, how do you exploit all of the information that the detector will produce? And that's not absolutely trivial. All right, so the detector is going to be in a very, very inhomogeneous radiation environment. You see there are 5 orders of magnitude of radiation damage between the innermost regions. And then as you go out and towards the back, the detector itself shields from the radiation. But this means that instead of spending too much money, because we're scientists, so we don't really have all the funds we ask for, this means that we have to put certain types of detector where the radiation is highest. So that's silicon sensors in green. And then where you don't need to put silicon sensors, we use scintillating plastic tiles and silicon photomultipliers, which are much more cost effective. I've learned that this is what project managers like to say. It's not cheap, because it's not cheap, but it's much more cost effective. And you can actually cover large surfaces. To give you an idea, there are 600 square meters of silicon pads and 370 square meters of plastic scintillator tiles. And this is being produced, the sensors are produced in Japan. The plastic, it was going to be produced between Ukraine and Russia, and right now it's neither in Ukraine nor in Russia. So it's also being produced in the US. Now, there are 2 sections here that you can distinguish. There is this thing that we call CE electromagnetic, E, and then CE, and then an H. The part that is electromagnetic, you will notice, is much narrower. It has many more layers, but it's smaller. This is because we use certain materials like lead and tungsten with a very large nucleus charge to force electromagnetic interactions. So most high energy electrons and photons, they will interact here and that's it. But hadrons, they interact via the nuclear force. So you do not really care about the electric charge. What you need to find is a nice nucleus to bang on and break the nucleus and produce hadronic interactions. So basically this part has to be much larger because hadronic interactions are not as easy to force. And we just want to have materials that have a very large atomic number that are dense. And so we basically have steel and copper. And yes, and then these are some, technical details. What matters is that in order to instrument the detector, we have to build 47 layers. And these layers, as you will see, are full of hexagons, which are the sensitive parts. The three different colors, you will see that they follow the radiation pattern. So in the center, we have thinner sensors, because then the probability of breaking it is smaller because there's a smaller volume of silicon. As we go further out, we increase the thickness. So these are 200 micron and these are 300 micron. So already just from this picture, we have three different types of silicon sensors. So three different types of things that we need to build. Then, if you look at the detail of one of these 60-degree sectors inside the layer, there's all of these electronics that need to be put together to connect everything. And each one of these boards is built in a different place. So for instance, these are made in France, these are made in Taiwan, these are made in Taiwan, these are made in the US, these are made in the US, and the green ones, the hexagonal ones, they are made in India. And they are also assembled in India. And so your colleagues here at TIFR have had a very important role in making that happen. As we go further back, you will see that we have even more hexagons. So these are very large layers. And then if you go to the very last layers, then you have much less silicon. And then all of these small tiles that you see here, these are all the plastic tiles. And the different colors just represent different boards that bring the tiles together. So, and they are done slightly in a different way mechanically. So you see they are divided in 30 degrees and then they are identical every 10 degrees. So this way you achieve a better modularity because you are further out, so you can do that. Now, this was what does it look like? What is its structure? And now I want to tell you a bit more about the active materials. So a silicon module is something that has a board with the electronics. So these are the boards that are fabricated in India. Then the silicon sensor is below. And in order to connect the two, we do this wire bonding. And this is a very standard technique. But building these boards was not easy at all, because you need to make a hole through the whole board, but then you need to put something here in the middle. So the hole on the top is bigger than the hole on the bottom. And the first boards that we asked the company to produce, they were actually bent like this. So it looked like a fruit bowl. If you put on the table, you could spin it and it would just spin. It was not flat. So this is something which we are now 5 to 7 years of gaining experience and working with PCB fabricators so that these things can be made. And then, of course, the return is that they learn how to do strange things and then they can apply it to other products. Then below, there is a sheet of Kapton copper foil laminate, which allows us to bring a high voltage to the back so that we can polarize the silicon and see the signals from the particles. And then at the bottom, it's a base plate, which is copper tungsten, that provides substrate to the heft. It provides heft to the modules. And here we cannot spare any millimeter with air. So that's why this base plate here is copper tungsten, but in other parts of the detector is actually made of titanium, but we even thought of making it out of just PCB board without any metal. You see that this is the stack up. So the electromagnetic section, you have 2 active sides around the same copper base plate. And there are many details of how to connect things. We are basically connecting to the back. We need to connect to something called the guard ring, which is a floating zone that you want to ground around the sensor. So this is a very complicated process. And there is also an effort here at TIFR to perform all of these operations of, let's say, making a sandwich, because eventually that's all it is. On the scintillator side, the situation is drastically different. So just to give you a comparison, there are 290 hexagonal cells, or half hexagonal or very cornery cutout, but there are 290 there, whereas here you basically have 64. And one tile board is this big, and one silicon module is this big. So the density changes quite drastically. So here, what you do is you produce these scintillator tiles, you wrap them with a reflective foil such that all the light is reflected and hits the silicon photomultiplier. So these are an array of these single photon avalanche diodes. So whenever you have light hitting, you produce an electric signal, and this then gets amplified by our readout chip. So in order to transform all of these electrical signals from the active elements into something that we can process as data, we need a readout chip. So this is the readout chip that was developed for the HGCAL. The physicists among you will notice symmetry. Why? Not just because nature likes symmetry, engineers also like symmetry. It's called copy-paste. So here you have basically two halves of the chip that are mostly identical. The only thing that is different is here in the central part. Everything else on the left and on the right is absolutely identical. And then inside each half, you'll see that there are several structures that are horizontal, that are replicated. These are the individual channels. So if we look at a logical diagram, what we have is that in each half, we have 36 of these chains that have a preamplifier, a shaper, and an ADC. And then if the charge is very large, since we want to have a very good sensitivity to the single electrical particle going through, minimum ionizing particle, the ADC will saturate very quickly. And then instead of measuring the total charge as a, let's say, amplitude, we just start discharging at a constant rate, and we measure how long does it take to discharge. So this is what we call time over threshold. And since we have to measure time, we also measure the time when it starts and the time when it ends. That's the difference that gives you the charge, proportional to the charge. But since we measure the time when it starts, this is also a great way of measuring when did the particle go through. So this is one of the things that we do. Then all of this goes into a buffer where the data waits for whether it's interesting or not. And this Dr. Shukla will tell you more about. Now, what is relevant here is that there is a lot of fast synchronous control, and then there is a part which is not synchronous, slow control, which is basically putting all the parameters. Because every time you make 10 transistors, they will all be slightly different. So the way to make them behave in a predictable way is to add circuitry that changes, for instance, bias voltages to each of the transistors, and then we can make it such that all 10 transistors have the same response. That's what we call trimming. Now, I'm not going to go into the details of what is in here, but one thing that is important is that this chip not only saves the data here for 12 microseconds, it immediately ships out a low resolution version. So the energy from several of those hexagonal cells is summed up and sent every 25 nanoseconds so that the system that Dr. Shukla is developing can have an idea of whether or not there's something interesting. And this is an important part that will come back in his side. Then, of course, when there is a decision to read out the data, we send a huge packet with all the details that are relevant for this particular collision. So this was the front-end electronics. This is what's happening in the experimental cavern. This is what is exposed to radiation. After that, there is the back-end electronics. And after that, there is something which runs in software. And to tell you all about the backend electronics, I will hand it over to Dr. Shukla.
Thank you, Dr. Dell.
If you call me doctor again, I will think that I'm my father. My father was actually a useful doctor.
Yes. So are you. Yes. So. Okay. So I'll start with a bit of brief introduction for backend electronics, what we do, essentially how we do this gigantic task of analyzing this data. This is the detector part, which Andre kindly covered quite nicely. To use this detector to make it effective, we have these two data paths. One is the DAQ path, where we have the fine resolution images of the detector, and other is the trigger primitive generator path, or the trigger path, which has these low resolution images that we create. The main difference between the two is the resolution of the image itself and the data volumes. Here, since we have to look at the data every 40 nanoseconds, the data volume is reduced by making the sums. While here we have more time to look at the data, get the data out, we have a more finer. So just to put things perspective, the DAQ path, which is the DAQ ATC cards, which goes to the hub and then the central DAQ, it's a very high large volume system. Right? On the TPG side, we have a low latency systems, and this is what puts a very large strain on designing such systems. The first part of the TPG, or the trigger boards, they do more of a decoding of the data. They streamline the data that feeds into the next stage, which has to do most of the processing that Dr. Andre talked about. And then this data is shipped to the level 1 trigger system, which puts the information from all the subdetectors together, which decides if the data that we're looking at is either remotely interesting. And if it proves to be interesting through the level 1 trigger test, the signal is sent back to the central DAC system, which gets distributed back into the DAC systems, and the data that was stored for 12.5 microseconds gets read back. So that's how we get the high energy, high resolution image. If the result doesn't come back in this 12 microsecond period, then the data gets overwritten and thrown away. Okay, that's how we are able to get the data out and stored. So the latency is one of the very critical thing here. There is another system, NZS. I'll not talk about it much later. What this does is there's another detector system, muon trigger. Again, Andre, when we showed you the CMS part, there was this new muon trigger detectors coming in. We are trying to also get a integration with that, so that when we get a muon candidates, we then send a special signal to the DAC system, and which then sends that signal to the front end system saying, give me little more finer image. So it's that image is even more finer than our regular system. So we can study these events in more detail. So this system is also being developed. Okay, just to put some numbers on what kind of data or what rate of data that we deal with. Again, this is what was promised in the title. From the front end, the DAQ system receives this optical links. Each of the link is 10 Gbps, and 108 such links are received per board, and there are about 100 such boards. Okay, then all the data goes to the hub card, as I said, which gets aggregated. There's 25 Gbps per link, and there are 12 links. And eventually, data gets shipped off in 400 Gbps large links. Okay, and again, hundreds of these links. Then in the TPG stage 1, again, we have this 10 Gbps uplinks. We have 120 per board, and then we have 16 Gbps links from stage 1 to stage 2. Again, 96 links per board, about 100 boards per of this stage again. And then NZS is much smaller system with 1 board per endcap, and so total 2 boards, and they just deal with that 25 Gbps input, and then about 125 Gbps links output to the DAC. So that's the whole system. That's how we have architected the system to achieve the processing. I'll try to then go into a little bit details of each of these things, not too much, to give you an idea what is happening within this. Okay. all of these boxes that I showed about, they have to be, a special board had to be designed. In general, a CERN-wide decision had been taken by doing different prototyping that we will adopt this advanced ATCA communication architecture, which is quite widely used in industry. This has been adopted, and then we have, of course, made a lot of modification on top. Through a lot of prototyping, we have come up with this Serenity platform design, and this implements a large processing FPGA and lots of high-speed optical links. So it's about this is an FPGA. Some of you who use this is a Xilinx VU13P FPGA with 124 high-speed links, each capable of about 28 Gbps. We use them at 25, and then there's a whole ecosystem about this. There is a common firmware for all the link communication protocols, and then there is all supporting software for all this. And TIFR has been a major part of this development, testing, and this thing. Okay, this board is being used not only in HGCAL but all of the detectors. And I think I forgot to add this. There is also a lot of interest of using this board in other experiments, and I think TIFR is also exploring possibility of using this in other steps. A bit of a history again, as I said, as TIFR was involved, this was a lot of design work. We have participated in prototype cards. We started in 2008, and we are now at the 5th or 6th revision, which started in 2024, and this is what the cards are being used. About 100 of these cards will be produced and assembled in India, and this is one of the things we were going up to different companies and talking about. And this effort is largely coordinated by TIFR and many of the people sitting in the audience. Let's look at the DAQ system a little bit in detail. It has, again, as I said, about 100 boards. They're divided into sectors, which looks at specific parts of the detector, about 120-degree sector. And then that data gets funneled into this 25 Gbps S-links, goes to the hub boards or DTH boards, goes to the central path. Overall, the point to emphasize, as I said, this is a high volume system. There's a 3 megabytes per event roughly, and the overall throughput is about 2.2 terabytes per second. Again, this is a sporadic system. You don't have constant data coming in. This data comes in only when you have a trigger coming in. So the nature of system is different. Internally, how this is implemented, this is all implemented in the central FPGA I showed you. There's a lot of firmware that does this job, and this has been written by different engineers who have been working with this with us. This involves designing the special capture blocks which filter the packets coming from the front end. They do some basic error checking. And then they join these packets together to create the bigger packets in the end. There is a slow control system, again, as you've heard about it. To actually control the front end, you have to program thousands of parameters in the system, and that's a huge task again. Then there is a fast command system, which is also quite unique. You have to be able to do a precision timing measurement of this 30 picoseconds or 25 picoseconds. We have to first synchronize everything. These about 120,000 chips have to be synchronized together to this accuracy, and for this, the timing distribution, the commands are sent again through this system. So quite, I'll not go into details of the cell. And then parallelly, then this is the trigger system that we'll quickly look at. We call this trigger primitive generator, and this is divided into 2 states. Before I start going into more detail, I'll just quickly introduce concept, what we call trigger cells. Again, Andre touched upon this, how we reduce the volume of the data by summing the individual cells. So this is a cartoon of the silicon sensor where each of these are individual cells. If we start sending each of these, we don't have enough bandwidth, we run out of time. So we sum them together, and this is what is being used. This is the currency for us in the trigger system. It all deals with trigger cells, and I'll talk about this trigger cells. Okay, again, the system is divided into web of boards. Talked about hundreds of boards in stage 1 and stage 2, about 100 boards in each. And again, the overall bandwidth is astonishing. So the data that is coming in is about 110 terabits per second. That data comes in. We filter that data, and then actually expand by decoding to about 114 terabits per second. And then finally, it gets filtered by looking at doing clustering, and which I'll talk about, to 14 terabits per second to the central DAC. So again, a huge high-speed data processing. The stage 1 largely does all the decoding of the data, which comes from the front end. It then does some bit of a computation for the partial trigger towers, and then it repackages all the data in a time multiplexing fashion. This is all done for the stage 2 system. The stage 1 looks at a small part of the detector, and that's how the system is segmented. But the stage 1 wants to look at a full slice of the detector to be able to do the clustering. Hence, all the time multiplexing, so that a stage 2 board can have more time looking at the data and can get data from multiple stage 1 boards. Again, the challenge is this has to be done within 1 microsecond. All the firmware, all the effort goes towards doing this in 1 microsecond, which is a bit of mind-blowing. The stage 2, now we start becoming even more complicated systems. Again, if we look at this as a simulation, the CMS, so the interaction point, and you see all the particles going through. This is what the tracks you get in the tracker, and the cones is what you have jets, and this is the deposition in the calorimeter, HGCAL. This is a high-resolution image, so you have so many small dots. What we get is a coarser image of this, and we want to reconstruct the properties of these blobs so that, for example, we can look at the jets. And since all the detector system is angled such a way that it all points to the interaction point, we can put together things from the tracker and calorimeter, and we can have a more complete overview of what's actually happening and can select such an event. Okay, so this is the part which HGCAL looks at. So this is what we are trying to do in the stage 2 of our processing systems. This shows a 120-degree sector. There is a 120-degree symmetry. So whatever is done from 120 degree is then replicated everywhere. So we just sort of show this. And this is divided into columns and then triangles. And this is all, as I said, a game of triangles and hexagons. So we put all these trigger cells which are sent from stage 1 part of the detector. They are seeded into these triangles, and we start constructing hexagons and eventually construct clusters. And this is a very, very complex process. So just to sort of confuse a bit of the things, this whole triangles, to do these things more efficiently in the firmware, these are put in a unitless projective space. All the calculations are done. And then this is not in the physical space, which makes things very non-intuitive. And the calculations for the cluster calculations are done in an even more different coordinate system, which is an azimuthal angle and a phi, which is along the detector. And to make the things even more complicated, we have to do this in 2 microseconds. So this is one of the, again, biggest challenge of the system. This is I've just put here sort of the algorithm in more detail, how it all deals with. Probably in the interest of time, we'll probably not go through this, what we're doing at the time. But it's a very complex process which requires a complex data routing mechanisms to be implemented, which are deterministic in real time, and then also doing seeding, finding clusters, and then finally getting the cluster properties from this. And for example, when the cluster properties block, which is what gets the final properties out, was developed by one of the PhD students who was working with us. The students have contributed quite quite heavily to such developments. Okay, this is the overall diagram. Cover this. So all this data is sent to the level 1 trigger system, which is what I was talking about in the beginning. The HGCAL is just one part of this. There is other parts of the detector, muon, track trigger, and this is all put together. And this system looks at the data as a whole, and then the level 1 accept signal goes to the detector. So coming back to our diagram, the level 1 trigger system sends the level 1 accept signal that goes back to the DAC and to the front end, and the high resolution data comes out, which then gets stored in the system. Now this is a big system. You have seen boards, this board, that board, and this speed, these many links, all nice. We can't start building everything just as directly as a big system. We have to start small, start testing these small systems. And so how we do this? So first of all, we did a lot of tests with individual communication links, protocols. We've made sure that they are robust, because if they have not proven to be robust, we can't really trust anything that comes out of it. So this has been a quite important thing. And we have been doing lots of system tests. So we started assembling bigger and bigger systems, starting with a single module, single tile board in our lab, putting them together and testing more and more bigger systems. So this involves a lot of communication with different boards as well. And then there are different auxiliary systems to support this. So we've basically gone from now lab test, we have done and then putting multiple such boards in beamlines. So there is a test beamlines at CERN, where it's not, of course, as powerful as LHC, but we can then put our system in beam, irradiate it, and we can see how the system, how everything behaves as a system, which is quite an important thing. The main thing is what we live by is we test further, and then we test a little more. And then there, of course, there is a lot of interval of time where we fix things, which is the most important thing. Just to give, this is where I'll sort of leave you with. These are the kind of test systems we've built to test. This is a few layers assembled here in a magnet, 3 Tesla magnet. And this is how the individual layer looks like. This all data is sent to the Serenity cards. Sorry, this photo is a bit older. And then you have a DTH card which aggregates the data, which goes to the PC. There is a whole slow control, fast command systems. There's an online control software. All these things are developed by different people. So when all this comes together, all the fault lines, of course, and finding them and fixing them in time, because you get 8 days of beam time. Doing this is a challenging part. And again, many of your colleagues at TIFR have participated, students, in this, and they can tell you all the horror stories about the time. And then finally, so with all the uncontrolled coordinates, everything else, and then we get this nice data looking like this. This is, for example, for silicon modules, you see the beam spot, you can see the beam passing through the detector, and then this is for the tile boards. Again, we are now building more bigger and bigger systems. This is just where it's all started. So it's the whole vertical slice, first time put together. And again, this work was quite monumental. I'll leave you here with Andre again. He will cover even more bigger systems and the more outlook.
Thank you, Raghu. You can have this. I can. All right. So as Raghu was saying, we put the systems together. And in one way, it's a process that's naively, deceivingly very simple, because the systems all look the same, except everything changes all the time. And this is because when you're putting things together and you join everything, basically the concept is always the same. You go from something that is on the beam to some software, but every time you do a different test, you are changing one piece or several pieces at the same time. And for those of you who have debugged things, changing many things at the same time is the absolute worst thing you can do, but sometimes it's unavoidable. So system integration is very important. And I just want to tell you a bit that we've started this a long time ago with pieces that had nothing to do with the final detector. but we wanted to see whether or not the detector would perform the way we thought. So we took prototypes for the electromagnetic part and for the hadronic part, and we exposed them to beams of electrons, muons, and pions. And this is what happens when you have an electron beam. You had a very nice, tight shower in the front. You see all of these hexagons, right? By now you know all of the hexagons. And this is the kind of energy linearity. So you see it's 1.5% at very low energies. It gets better with higher energies because you get fewer fluctuations. Yes, and there is a plot here, which is the energy resolution, and I don't know, the dog ate the homework. And this is the pointing precision, because since you get a shower, the development of the shower, you can also know the axis of the shower, you can measure the axis. And if you do the same thing for hadrons, now you have pions, you will notice that they don't shower in the same way. And a lot of the showering happens in the hadronic section. And then there was work which was actually performed by someone from India, Alpana, on the dynamic reduction networks. And you can also ask Rajdeep about it, which actually perform better than in terms, so this is the relative resolution, the energy resolution, and they were much better than the traditional chi-square method. And this was an interesting work because you wanted to figure out which part of the information was relevant for the improvement. Okay, so these are the results in timing. So we managed to have very good timing resolution, such that we made this sort of movie of the shower developing. And I still remember as a physicist when we first looked at the timing of the hits, and there was this sort of straight line, and when we looked at the slope, it corresponded more or less to the speed of light. And so when a physicist finds constants of nature in their measurements, there's always, I don't know, some heartwarming feeling. Now, we had also in the beam a reference. So we did the timing resolution as a function of the energy, and we actually found back something like 20 picoseconds. So all of this gave us a lot of encouragement to go from the thing that is here on the left, that was this small, to something which was much larger in 2021. And basically since 2021, we've had iterations of the final system. So this is what we had at the time. This is the signal. You have here the signal from muons, and this is the noise. So we have a very nice signal over noise. And then we also looked at the performance for Sipa-Montile. You see very clearly also the MIP signals again. So the scintillators have a much larger signal over noise, which is good. And from here, we've just been building bigger things. We chained lots of modules together. And then we've attacked one of the nastiest things in this project, which is that there's not only one type of hexagon. If you work in HGCAL, you learn that there are 13 types of hexagons, because sometimes you have to cut them like this, sometimes you have to cut them like that, sometimes you do not fully cut them. And why? Because you need to cover all of the edges around the circle. And this is what happens when you have to connect to these modules. So you have a board here, a board below, a board above, and then the board at the bottom. And yes, if you're asking yourselves, no, these are not the screws that we are going to use at the end, because they have to be flat in order to fit within the 5 millimeters thickness where particles don't do anything. In order to cope with all of these varieties, you see already here there are 1, 2, 3, 4 different boards, but we have many, many other boards. All of them have a QR code, but all of them also have an icon. So we can say, can you please get me 2 pineapples, 4 grapes, 3 hearts, and a scissors? Okay, it's much better than saying, get me a 3xF1, etc. For your information, we have one type of boards that it's all fruits: the pineapple, the grapes, the apple, the avocado, and the donut. Okay, so I don't know if somebody here thinks that donuts are fruits, but apparently it goes into the set of fruits. And I'm pretty sure that some GPT large language model will learn that donut is a fruit because of this. All of these parts get stuck together, have to fit into the 5 millimeters. You see here, this is a silicon module. You see there the sensor. This gray line here in the middle, it's the sensor. This is the base plate. This is the cooling copper plate. And then on top of it, you have this board, the red board. This is what we call an engine. And the cutout of this as all to be simulated in 3D CAD by people who actually understand mechanics, not physicists. Sorry, production mechanics, point mechanics, Lagrangian mechanics, sure. Because you have capacitors, and then these capacitors, where they go is determined by electronics engineers, because the capacitors cannot just go anywhere. And then on top of this board goes that board, and behind it comes the power, and you see this pipe over here, it's just blowing dry air so that we make sure that there is no humidity in the volume. And of course, we have a lot of help. There's an advantage to being Portuguese in these experiments. It's very hard to hit your head in places. Being short is very helpful. So you see here that it's really nice to be small and be able to get all of these cables to places. And then we bolt everything into place. And in fact, as we are here, we are starting to turn the first double-sided layer, and hopefully nothing will fall, because you need to bolt everything down and then you turn and then you build the other side of the layer. And then sometimes, we don't take it through the traffic of Mumbai, but, we put the detector on some shelves at the back of a car. And this is how they were brought to the beam. And then you'll see here the experts looking at the electronics, admiring, I don't know, optical fibers and things like that. All electronics engineers, all experts on these things. And so eventually the last challenge, and I'm not going to go very long on this, is how do we get the electron out of the 200 pileup interactions? Because there is an electron there, a high energy electron, but you need all of the information. And here, for instance, you do not see the timing information, but that is also available. And there are being two largely separate efforts. One of them based on more traditional techniques of going layer by layer and performing clustering, and then taking these clusters of the different layers and connecting them together. And this has been developed in a very modular framework. So after every iteration, you can add some algorithm. So for instance, there are DNNs that are being used to regress the energy of the particle. A different path has been taken by a group of people who just said, we just take all the records, all the individual information, throw it into a graph neural network, and it will tell us which particles were in the event. As you have guessed it, this did not really work out of the box. It's still computationally very hard in the sense that you cannot fit it within the 20 milliseconds. So Raghu told you about 12 microseconds. This is to select 750,000 of the pictures, to take the high resolution pictures. We cannot save the 750,000. We can only save about 10,000. So in order to save these 10,000, we run on normal computers with GPUs. But this sort of algorithm is not yet feasible within the 20 milliseconds that we can run things through. Anyway, the conclusion is that there is a lot still to be done. We are only now starting production. Production will go on for the next 2 years. And then there will be another 2 years where we try to figure out, does it actually work? And then it will be underground, and then there will be collisions, and nothing will make sense. So I'm pretty sure that if I ask ChatGPT to make the detector work, it will say, I'm sorry. So we need humans, we need people with brains and arms to make this thing work. So with all this delay, thank you very much for your attention. Yeah. Yeah, go ahead.
Hello. So with so much electronics packed in a so much dense space, how do you cool them? And what is the typical power consumption of this? Like how much heat you need to dissipate?
That's an excellent question. So we cool it very carefully. We keep the detector at minus 30 degrees, not because of the electronics, but because of the sensors. So it reduces the radiation damage to have them cooled. As far as I remember, the detector is each one of the end caps, I think it's about 100 kilowatts. And that's one of the requirements for the electronics. Each one of the channels cannot be more than 1 milliwatt. I think it's something like that. So everything has to be thought through from the beginning. And recently, when we learned that there is one of the digital chips that had a problem, we had to go and measure again what is the consumption, how much power is it taking in the different operating modes. And then we feed this into a model, which in this case, I will confess it's an Excel sheet, to figure out what kind of power you get. Another thing that happens also in power is that there is power dissipated in the cables that bring the power. So that needs to be accounted for. And the amount of current for the different places is accounted for in the diameter of those cables because you don't have a lot of space. So in the beginning, physicists thought that you could just bring the power with five, cables, normal copper cables. And then we decided to go with something which is much better, which are these laminates. Yes. So this sort of, you see the brown stuff, which is connected to the wires. So there was an engineer who came in and said, no, you physicists, you don't understand anything. There is this thing which is much better. And you can actually just bring a lot of power through that without many losses. Yes, it's a bus bar. And then concerning the cooling itself, it's a two-phase CO2. So it's a liquid gas mixture. This is something that we have actually have a lot of expertise at CERN for. Because CO2 is really good for the environment. Not in your bedroom, but...
Okay. Yeah, I have a couple of questions. First of all, thank you for a very nice talk and such a building, such a complex system. One question regarding the observer where you are using copper, tungsten or lead. Why not only tungsten? Because tungsten has a higher density. So you can use, okay, so any reason for that using copper, tungsten or lead?
That's a very good question, to which I do not know the full answer, but being a physicist, I will try to guess. So part of the reason for lead has to do with the surface. So every one of these cassettes, and the cassette is like from here to Raghu, they have to be completely covered. And it's easier to machine the lead because you heat it up a little and then it gets, it's conformal. Tungsten, yes, it's very nice, but I have some tungsten plates that we use for the beam tests that have very sharp corners. And whenever we hold that, I have to explain to people that one, it's heavy. So before giving it to them, I make sure that they hold it on top of some surface. And I don't know if there might be some economic reasons for that. Because for instance, with the lead, we need to be careful. We have to put like a very thin stainless steel cover so that people don't go and lick the lead. For the copper tungsten, it's a good question. I think it has to do with the ability to machine it. Because tungsten itself is very hard to machine. So if you make the alloy, then it becomes more malleable, more suitable for machining.
Yeah, I think, yeah.
Anything else? No.
Yeah, the second question regarding the plastic scintillators. What is the typical dimension of the plastic scintillator you are using?
So those vary between 2 by 2 centimeters up to 6 by 6. Yes, so they change drastically. So the physics in the collider has a very strange geometry. So the amount of phase space, let's say physics phase space covered by this square here is equivalent to the amount of physics phase space covered by that square over there. And it's the equivalent. So in here, it's a cell that is this big, so half a square centimeter. So it's the density is very inhomogeneous, which is also why the radiation field is very inhomogeneous. But the scintillators go from 2x2 to 6x6.
So yeah.
The thickness of the scintillator? No. It's thinner. Yes. So I think it's something like, don't quote me, but I think it's like 3 millimeters, 4, 5.
Yeah. I think
because you see the scintillator plus the board, they have to fit on the 5 millimeters. So it's going to be that order of magnitude.
The SIPM there is about.
You have to, the microphone is not to point. To point to your mouth.
The SIPM here is about 3 mm by 3 mm. So you can get some idea of the scale.
So in terms of radiation hardness, the plastic scintillators are not prone to radiation hardness, or compared to the silicon detector, or other way. Okay, I just want to understand.
I mean, the cost is a main.
The cost is one factor, but if you talk about the radiation hardness, so these plastic scintillators are not affected by the radiation hardness.
It is. So they are
For example, we have seen this in nature.
Okay.
No?
They are, but they are put in the part. I think what Andre was trying to show here is that that's why we put them in the low radiation environment zone. So even if they're affected large, because the volume of the scintillator is much larger than the silicon, the thickness, if we put them in the low radiation zone. So we compensate for different.
Right.
Yeah,
So basically, you can think of this as follows. You start from where the radiation is the lowest, and you ask yourself, what is the material that is going to work here? And the answer is plastic scintillator will work. And then you keep going up, you keep going up the gradient of the radiation dose, and then you reach a point where if you run for 10 years, then you see this boundary between purple and green. That's the boundary where we expect after 10 years that the plastic will not have a good enough signal over noise. At that point, you have to switch. And there you switch to silicon. Perhaps we could have a third technology, but then it would make the project 50% more complex at least, because you go from 2 to 3 technologies. So we decided this is a balance, but here we decided to just have 2 technologies. And then even within the silicon, you see that here it's 300 micron thick sensors, because after 10 years, signal over noise. In a higher radiation point further into the detector, it's 200 micron because signal over noise. And at the very innermost part, it's 120 micron, again, because of the signal over noise. And this is not linear at all, because the radiation field, as you can see, is very much not linear. So we adapt and we try to reduce the number of varieties to keep the project feasible.
Okay.
Maybe, yes.
Regarding your energy resolution of the single particle, what would be the limiting luminosity? Up to what luminosity it is valid?
Okay, so if I understand correctly, your question is a question of aging.
No, not aging, not question of aging. It is overlapping showers.
Okay. So you mean in terms of instantaneous luminosity, the pileup?
That's right.
So I'm generally a skeptical person who prefers to measure first and quote later. From simulation, we should be okay with a 200 pileup. So the LHC, in the beginning, there was an idea of having a 140 pileup and then 200. We don't know exactly how it's going to evolve, but I don't want to extrapolate from the LHC. But the LHC detectors were built for pileup 20. And we had a bit of an upgrade in 2016. They are now working with pileup 60. So that's a factor of 3. I don't think that we are going to be able to deal with a factor of 3. But if everything works, and as we learn to operate the detector, it may be possible to go higher. Also in the sense that, so this was something that was done at LEP. When you know that the accelerator is going to end, you just crank it up and you burn it, and you find where the limits are. Because if you don't do that, there's no value to just saving an old detector. You really just go deep and try to figure out where the limits are. And this way you also learn where the limits of the technology are. And this is important because there are actually plans now to go beyond the LHC. And I just wanted to give an idea. So there is a proposed project. So the LHC is the small thing on the top to make a 100-kilometer long collider. And this time it would actually go under the lake and it would go. So you see, this is a mountain.
Yeah.
So instead of going under the mountain, it just goes around the mountain, just totally avoids the traffic of the mountain. And it just goes around and stays in the soil. So this is something which is being considered, and we will need detectors that work in that thing. So it will be important to find out where are the limitations for silicon.
Okay. Maybe I'll have one question more towards Raghu. In terms of the design consideration or challenges, there's two kind of boards, right?
Yeah.
TPG versus DAC.
Yeah.
So are there something we can say that one being more complex than the other in terms of the design thing, or as an engineer point of view, you find both of them are at a similar level, or what is
Yes.
the?
So there is two things. One is the hardware, and then there is a firmware, which actually defines how the board behaves. The complexity ways, I would say both have different challenges. They're equally challenging, and most of this complexity is actually hidden in the firmware. Physically, hardware-wise, the base boards are identical, and that is by design, so that we want them to be generic, not only across HGCAL, across different detectors and different experiments. So it's to make it more generic. And then the only difference is the optical IOs that we connect to the boards, depending upon where are they being used.
So why this sorry. So why this frequency is 40 megahertz or every 25 nanoseconds this collision happens? Any particular reason or some past data?
If Andre might be able to answer that better, but if you see, there was a note in the
Microphone in the
Sorry.
mouth.
If you see, there was also a note in one of the slides.
Which one?
For the high-lumi LHC initial.
Yes. I'll get it.
Yeah. That it's almost impossible to run at 80 megahertz. But anyways, elaborate a bit more. Why? Yes.
So every accelerator has a range of parameters. One of them is, let's say, the duty cycle. How often do you get collisions? And this determines a lot of things for the readout. The other one is how spaced. So one thing is within, let's say, several bunches, and then how often do you get those repeating? And this spacing is what gives us the 40 megahertz. Now, in the late 90s, when the 40 megahertz were thought of, it was a big revolution. It was much faster than anything else that existed, but people were extrapolating the possibilities of electronics. The counterpart on the accelerator side is the accelerating structure. So the radio frequency, the microwave radio frequency structures. So the LHC uses 400 megahertz accelerating cavities. So what happens is that the protons are in one of 10 RF buckets. And then this repeats every 10th. So if you would go and tell the machine, I want something, blah, 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 the machine will say, well, we can only do so much with RF frequency, or it becomes much less efficient. So there is a, when you design an accelerator, there is always input from the accelerator side, input from the experiment side, in order to try and find a specific thing that works for everyone. Why 40 in particular? I'm sorry, I don't know. I was in high school. No. The thing that, and you know, I don't know if many of you are physicists, the thing that I really find interesting about the LHC is that when the beams go in, they have 450 GeV, they come from the SPS. So the revolution frequency is 40.000 something megahertz. And when you accelerate the particles because of special relativity alone, the frequency changes. So all of the electronics in the LHC are changing their frequency synchronously as the beam particles are accelerated. And that's, you know, one way of seeing Einstein is right.
That is why even when we are setting up the run, there is actually a ramp of this frequency and ramp down. So 40 is not a 40. It also actually changes. And we have to design our boards, our clocking networks, everything, which handle these ramps of frequency ups and downs. So that's
yes. And for the physicists and the engineers, there was a chip that had a locking range, which was supposed to fit all of this. So it's called, it was a PLL, okay? And there was one detector, which unfortunately was the one I was working on, which had 3,000 of these chips. So what happens because of statistics? Several of them did not really lock in the range after 10 years of operation. So whenever we would have a ramp of the LHC, our detector would go out of sync, and then we had to reconfigure it. So, you know, when you make many of something, you are definitely going to get things in the tail, and that's, you know, it's important to test and this is the part that is very difficult, is that you don't know exactly how things are going to age. It's like people. You never know if they are going to become nicer or nastier as they age.
Okay. You had a question? Or okay, so with that, let's thank both Raghu and Andre for excellent.
Thank you.
Okay,